So now that you've seen how to add matrices, multiply them by a scalar, subtract them, comes a time where we have to talk about matrix multiplication, and we have to figure out like what's a practical way of defining matrix multiplication. By practical, I mean something that's going to be useful. I don't want to define matrix multiplication in some way and never have to use it again because it never applies when I want to solve problems. So for instance, if I have a matrix A, which is 1, 2, 3, 4, and maybe a matrix B of the same size, right? The 5, 6, 7, 8. So it could be tempting just to define A and B by the matrix of the same size that I get by essentially multiplying components together. 1 times 5 is 5, 2 times 6 is 12, and so on. So that could be a way of defining a matrix product. There are some applications where this is required, that we need to multiply this way, matrices, but they're actually quite rare. So there are a lot more problems where we actually want to multiply matrices, and that's not the way we want to multiply them. So we'll see where the notion of matrix multiplication comes from. So this isn't something we don't want to do in this course, multiply component-wise. Not very practical. So to introduce the concept of matrix multiplication, strangely we have to review the concept of composition of functions. They're actually quite related. So recall the composition of functions. We see those a lot in calculus in particular when we want to differentiate complex functions. So for instance, let's say I have a function f of x, which is x squared, and a function g of x, which is 2x plus 1. I can actually combine these two simple functions together in order to form a more complex function. How do I do this? Well, I could actually look at the function f of g of x. So which function is that? Well, g of x now becomes the input of function x. Essentially because we take x, but we apply g first to it. Okay, so maybe on a diagram, I take x, and the first thing I do is I apply function g, and from this I get g of x. And then g of x becomes the input to function f, and then I send that into the input of f, and what comes out of it is the input squared, right? It's the input squared that I get. So I get 2x plus 1 squared. So I get something that's slightly more complicated than f and g. So on the diagram, I take g now, and I send that into function f, and what comes out of it is f of g of x. So in this case, for our example, it's 2x plus 1, and here it's 2x plus 1 squared. Now this function, f of g of x, we could give it a new name, like h of x, but it's also interesting to give it a name that's based on f and g. And the name we use, and the symbol that we use, is f dot g. So it's an empty dot, and you should have seen this in calculus and in high school. And why is it f dot g? It's because it's remind us that it's equal to f of g of x. You see the letters here appear in the same order. However, on my diagram, so this is now function f dot g, right? I take x, and what comes out of it is 2x plus 1 squared, f of g of x. But you'll notice that now the order, right? The g here, which was applied first to h, of course it goes here, because in my notation here, g is, this is going to be, when applied to x, this is going to be f of g of x. So I want g to be applied first. So that's why they're kind of written backwards. Let me erase this now. Right, so the function that's here goes to the right of the dot, and the f that acts last goes to the left of the dot. Okay. Let me erase these arrows. I'm trying to. Okay. All right. And all right. So this is a little review of function composition, composition of functions. So let's try to answer the following problem. I'm going to write it down. Which standard matrix is that of a linear transformation that performs a clockwise rotation of theta followed by a reflection across the x-axis? So what is that question about? First of all, there's a new word here, standard matrix, that I didn't define in previous videos. A standard matrix is, if I have a linear transformation, I can write it in the form a matrix times x, so x being the vector of unknowns, and that's the standard matrix. Okay. Now we have seen the standard matrices for the two transformations that are that we talk about in the question. So that we've seen the standard matrix about that performs a clockwise rotation of theta, and we also saw the standard matrix of a reflection across the x-axis. So maybe let's start by writing those down just to remember what those are. So so if I want to do a clockwise rotation of theta degrees, okay, let's call that transformation T1. Okay, T1 of x, and we saw that the matrix corresponding to that linear transformation is the matrix cos theta sine theta. So this is what we saw in a previous video. Okay, times x being a vector, right? So we also have the a reflection across the x-axis. Let's call that one T2. Okay, so it's the second linear transformation. Which appears in the question. Okay, so this is the standard matrix of that linear transformation. Okay, and what we want to do is we want to rotate and reflect. Okay, so graphically what's going on, essentially I want to take a point or a vector, rotate it by theta, and then reflect it. Okay, so it's a two-step process, right? Rotate, well actually, maybe I should write rotate like this, and then reflect. And what I'd like to know is there a linear transformation, or in particular, and what is the standard matrix of that linear transformation that will allow me to actually know how to get from the first point to the third point directly. So I want to essentially find the composition of these two linear transformation. Okay, so let's take a look at that. Okay, so first of all, okay, if I take a point, okay, so I'm gonna let x equal to the vector x1, x2. Okay, could also write xy. Maybe that's better because we're just working with points in R2. So okay, I can use just x and y. So is that going to be confusing? Maybe, yeah, because there are two x's here. Okay, so I'm going to switch back to x1 and x2. So this way there's less confusion, I think. Okay, so first thing is we take x. Okay, and then we want to rotate. So if we rotate, we apply function T1. Now if we apply function T1, we're going to get, let me rewrite the standard matrix, cos sine theta minus sine theta cos theta, which we multiply by x. Okay? So previously, okay, we had our g, that's like our g of x, right? So this is actually, maybe let's rewrite it here. This is actually t1 of x. So I've got t1 of x right there, okay? Oh, and I'm gonna want to give those matrices a name. So this one I'm gonna call it B, okay? And this one I'm gonna call it A. Maybe let's put X in bold again, just to remind ourselves this is a vector. Okay, so what do we have here is maybe let me write it here. T1 of x equals B of x. Okay, equals this. So this is the B. Okay, and then I take, so this is going to give me a vector. Okay, if I multiply this out, this is going to give me a vector. I take this vector and then I apply T2. T2 will reflect it across the x-axis, right? So maybe even like to remind ourselves that I'm doing the rotation and a reflection afterwards. Okay, and if we go back, right, T2 is T2 of x is A times x, but now my x is all of this, right? It's this, because this is the input now. So I send that into T2, and what I get is A. So I'm going to get here T2 of what? Of Bx, but T2 is A of Bx. And that's, okay, let me write it here. So A is 1, 0, 0, minus 1. That I'm going to multiply by Bx. Let me rewrite it here. Cos, okay, x2, all right. That's it. That's what I'm going to get after composing those things together. Okay, now I'm going to evaluate this. Okay, this thing here, I'm going to evaluate it. But before I do this, I want to explain why, where the matrix multiplication comes into play in here, or how we're going to define matrix multiplication so that it becomes useful in this context. So what we're doing here, right? We're taking, we're doing T2 of T1 of x. That's what we're doing. We're applying T1 first and then T2 afterwards. So in fact, what we're doing a composition. Okay, as we do this, right? This is a composition now. Okay, we do T2 dot T1. We see we have to reverse the order of T1 and T2 because T1 is the thing that acts first. So this is T2 dot T1 of x, of vector x. And what we get from this is T2 of AX, and we get, no, BX, sorry, T1 is matrix B, BX, and T2 of BX is A of BX, A times the vector BX. And essentially what we'd like to do, figure out, right, we'd like to come up with a matrix. This is what we're looking for. Okay, the question is asking, what's the standard? Could I replace all this by one matrix that multiplies x? So instead of having having to calculate bx and then multiply that by a, could I actually just multiply x by what? Single matrix? Because you see here, I have to do two matrix multiplication, right? Two matrix vector multiplication, essentially. And I'd like to replace this by one matrix vector multiplication. That's what I'd like to do. So the question is this possible? Could I figure out essentially the standard matrix of this composition of two functions? Okay, can I figure this out? So, okay, so this is what I'm going to try to do here. Okay, So I'm going to expand this, you'll see. So first I'll calculate what bx is. So what's bx? I multiply everything together. So here, to do my matrix multiplication, I could do a linear combination of my columns, of the columns of B, or multiply, you know, to get this, the first entry here, I have to do cosine times x1 plus sine times x2. So let me write that down. So I'll get x1 cosine theta plus x2 sine theta. So that's the first entry of this vector. And then here, this is going to be minus x1 sine plus x2 cosine. Again, by multiplying essentially the second row of matrix B against the vector x. So this is a vector now, right? Okay, so I've done one matrix vector multiplication, and I'm going to do another one because I've got a matrix here times a vector. Okay, so I'm going to redo this. Okay, so what I need to do now is 1 times this plus 0 times that. Okay, so essentially I won't have to do the times 0 because it's going to be giving me 0. So 1 times the first entry just gives me this. Okay, and then same thing for my second entry. It's going to be 0 times this guy minus 1 times this guy. So that's going to give me minus 1 times the second entry essentially. So x1 sine minus x2 cosine. And then I get a vector, right? This is a vector now. So this is where this vector is where this point is mapped. So this point is mapped onto this point essentially. So if we go back to our diagram, we see how any point here is going to be mapped onto another point. So now I know exactly what the formula is to go from one to the other directly without having to go through through this point in between. But I'd like to write it in this form so that I know what my standard matrix is. So what I'm going to do is rewrite this so that this is a matrix times the vector x1, x2. Now remember, a matrix multiplication is a linear combination, right, of vector of the columns of the matrix I'm looking for, and you can see that here I can write this as cosine times sine times x1 plus sine theta minus cosine times x2. So I've got a linear combination. So this way I can write it as a matrix vector product minus cosine times x1, x2. And that's exactly the matrix I'm looking for. So this is the matrix I'm looking for here. That's the standard matrix of the linear transformation that corresponds to the composition of the two two previous linear combinations. So the answer is, so actually we found the answer to our question. It's going to be cos theta sine theta minus cosine. Now, to come back, this matrix here, okay, we could give it a new name, like maybe C, but also it's not interesting to give it a name that's based on the previous matrices A and B that it's obtained from, and we're going to call that the matrix A times B. So essentially, when we write AB, it's because we're trying to remove, well, we're using this notation because it's as if we're removing these brackets, and then we're grouping these two together. So that's why we call it the matrix A times B, because it comes from the composition of two linear transformations with standard matrices A and B. And when we compose them, we get A bracket B of X, okay? And then if we drop the bracket, we essentially we get we can write this as ABX, and then essentially the standard matrix we're going to call it AB. So this is where it's coming from. So this is A times B here. So that doesn't really tell us how we multiply matrices together, but it gives us an indication where it's where this is coming from. So in the next video, we're going to go and look at two arbitrary linear transformations. It's going to give us a better way of understanding where how we can actually come up with a formula for multiplying two matrices together. Maybe what I'd like to end up with is just to show you that this standard matrix that we have here really works. Okay, just give you an example. So suppose the rotation that I do first is a rotation of 45 degrees. Okay. Well, we can look at what should happen to a point. I'm going to apply it to the point minus 1, 1. Okay. So I'm going to choose the point minus 1, 1, which is right here. Minus 1, 1. Okay, so what I want to do first is rotate, and then after that I want to reflect. Okay, so if I rotate by 45 degrees, so I've chosen a point that's kind of nice because it makes a 45-degree angle here. So the length of that vector here is root of 2. So if I rotate, so I apply, what's it called? I apply T1. I'm going to end up here. So I'm going to end up at, so this has x value of 0 and a y value of root of 2, because as you rotate, the distance to the origin of that point is not going to change. So 0 root of 2, and then after that we are going to reflect across the x-axis, so that will take us down here. So at 0 minus root 2. So this is by doing T2. Okay, so what you have here is what I was trying to illustrate right here, but with actually an actual value of theta and an actual point. Okay, and what I want to show you is that the matrix we got, like the matrix AB, will take us directly from here to here in one step, just verifying that it actually works. So if I do AB times the vector, or the point minus 1, 1, let's see that we're going to get the point 0 minus root of 2. Let's see that it takes us where we want to go. So we do cos theta sine, well actually, okay, I'll write it like that. Sine theta minus cos theta. The next step will just be to replace theta by 45. Okay, now if you replace theta by 45, cosine of 45 is root of 2 over 2. And sine of 45 is also root of 2 over 2. So that's going to be root 2 over 2 minus root 2 over 2. So this is a matrix that we multiply by this vector, and we should be getting the point 0 minus root 2. Okay, so because this standard matrix is supposed to represent the composition of the reflection followed by of the rotation followed by the reflection. So if I multiply these together, how do you want to do this? We could do this as a linear combination of the entries of the vector, or just multiplying by multiplying the entries of the first row to get with the entries of the vector and add them up. So I could do that. I'll do it like that. So it's going to be minus root of 2 over 2 plus root of 2 over 2. That's my first entry. And I do the same with my second row, right? I take the entries of the second row and multiply them by the entries of the vector and add those up. So I get minus root 2 over 2 minus root 2 over 2. And as you can see, the first entry is 0. And minus root 2 over 2 minus root 2 over 2, that's just minus root 2. And indeed, you see, we get the vector we're expecting to get. So we can see that AB, the matrix AB, does its job. It actually takes us directly from a point to the point you obtain after rotating and reflecting. So next video, we're going to show what the formula is when we multiply two matrices together.